Hello spooky Orgo people! Today we're going to do oxidation and reduction reactions, and along with that I'm going to give you a little bit of information about hybridization as well as reactivity of carbonyls. So let's get to it! So the first thing we're going to cover today is oxidation and reduction. We actually already did oxidation in the last chapter, but we're going to review it a little bit again now. And so first thing is first, I have this scheme written for you guys. And we're going to define what is oxidation and what is reduction. When we go from an alcohol to an aldehyde, that is going to be oxidation, which I will write as ox. And so we know that going from an aldehyde to a carboxylic acid is also going to be an oxidation reaction. So the definition for an oxidation as far as this class goes is when you add more bonds to the oxygen or to any electronegative atom such as nitrogen, phosphorus, sulfur, anything like that. But as far as this class goes, we're just going to stick to nitrogen and oxygen. The opposite reaction would then be the reduction. So for example, going from a carboxylic acid to an aldehyde, and then from the aldehyde back to the alcohol, and we're going to say reduction on the bottom. And I always like to code red as oxidation and blue as reduction, even though we call that red, but whatevs. And so the definition of a reduction for this class is essentially just adding more bonds to hydrogen. And that's your basics on oxidation and reduction. If we go more in depth into oxidation, we're going to first talk about the different reagents, and then we're going to use them up here in reactions. So we have all of these examples for reagents, and the thing I want you to remember first and foremost is that we have two weak reagents, and we have a rule that helps us talk about all of our strong reagents. So our weak reagents are going to be PCC and the DMSO reaction. Strong, anything with 4 or more oxygens is strong. So all of the rest of these answer choices will be strong, as I've written here. The only one that doesn't do the 4 or more is this last one, chromium O3 with H2O. Yes, that's still a strong oxidizing agent, but it's not that big of a deal. Now, when we put these into a reaction, we kind of understand what the difference between strong or weak is. First and foremost, I want to reiterate that there's no example of a tertiary alcohol here because oxidation cannot happen with a tertiary alcohol as far as this class goes. Here, I have given you examples of a primary, another primary, and a secondary alcohol. And so as we see here, in this first reaction, the alcohol will be changed into an aldehyde and then into a carboxylic acid. So in order to undergo both of these steps, we need a strong oxidizing agent, and we can use any of the ones from the list below, and that's why it will go to a carboxylic acid. In the second example, we stop at the aldehyde, so we need a weak oxidizing agent. For the last one, we're actually using a secondary alcohol to start off with, so we're always going to get a ketone. So either kind of reactant will give us a ketone. And the reason for this is because we're never going to get rid of carbons. We have 2 carbons, we need to finish with 2 carbons, so that is a ketone every time. So on the side, I'm just going to summarize primary OH with a strong oxidizing agent gives us a carboxylic acid versus a primary OH with a weak oxidizing agent We'll stop at the aldehyde. Conversely, a secondary OH with strong or weak will always give us a ketone. As far as reaction mechanisms go, you don't really need to know it. All you need to know is the starting material and final product, and then these reagents right here. And that's pretty much it for oxidation. Next up, we have reactivity of carbonyls. And when it comes to reactivity, we're going to consider two main things, which are sterics and electronics. So I'm actually going to flip to a clean page just so I can explain the steric and electronic effects, and then we'll jump right back here. So here we go. So before we go into steric and electronic effects kind of in depth, what you have to know first is what we mean by reactivity. So whether we're looking for a nucleophile or an electrophile. Well, in most cases in organic chemistry in this class, you need to know that the electrophile is going to be the carbonyl because it's what's being attacked. And while, yes, the oxygen here will tend to be protonated, it's not going to be a nucleophile. The carbon here will act as an electrophile. And the reason for that is because we have a delta minus on the oxygen and a delta plus at the carbon. So let's write that as our first note down here. Carbonyl equals electrophile most of the time. So when we want an electrophile, we are looking for something that is attackable and has a positive charge, because the less electron density, the more likely it is to be attacked. Now, as promised, steric and electronic effects. So next we're going to mention steric effects. So when we're talking about sterics, as we said, we need an electrophile, so we want the least amount of hindrance. So the less hindrance we have, the more reactive we will be. So in these cases, we can already see we have a huge oxygen group and a normal carbon group. Normal carbon, teeny hydrogen, normal carbon, normal carbon, normal carbon, a huge bulky oxygen group. So just looking at steric effects, we could say automatically that this will be the number one most reactive. But what if we want to prove that further with electronic effects? Well, we definitely can do that. And electronics is a huge umbrella term for a lot of things. It can pretty much be used to explain anything. But in this case, when we say electronics, we mean charge. So we want more positive charge equals more reactive, aka less electron density means more reactive. And if we look back at our molecules here, I'm going to zoom right in. We can more specifically talk about the donating effects and the resonance effects. So carbon is going to, or CH3, is going to donate a little bit of electron density. And in addition, we will have some resonance. The biggest resonance effect will be felt from these oxygen groups because they can throw these electrons on there. My screen is lagging a little bit, so I apologize. But when we resonate these electrons up to the oxygen, our electron density is flowing through here again. So we'll actually have a really high electron density at the carbonyl carbon at any given time. So we know that these two are going to be more reactive than any one that has an oxygen in it. And between these two, we can see that there are only one donating group versus there are two donating groups on the ketone. So this one has more of a delta plus, and this one has less of a delta plus. So again, we can see that this is the number 1 most reactive, number 2 most reactive, and then the two oxygen ones are almost the same, but we're going to say that this is 3 and this is 4. But again, they're almost the same. So don't get too stressed between nitpicking between the two of those. So there we have these effects. Along with these, we are going to now split this up into 2 groups. And the reason I'm doing that now is because it's really helpful for reductions. So I'm going to go ahead and make group 1 and group 2, and they're going to be split up by their reactivities. So I have written here the differentiation between group 1 and group 2. And again, this isn't something that is like a real chemistry way of thinking about things. Like, this isn't something you'll find in your textbook. It's just how I like to split things up because it makes more sense in my head if we have these categories. And just to reiterate one more time, group 1 contains aldehydes and ketones because those are the more reactive electrophiles. And then group 2 is the carboxylic acids and esters because they are less reactive. And one difference I want to point out before moving on is that group 2 has a leaving group. And having a leaving group will actually mean that it can undergo multiple rounds of a reduction reaction. And if that doesn't make sense, that's okay, because we'll go over that in a second. But just to reiterate one more time, having a leaving group means that group 2 will undergo multiple rounds of a reduction reaction. So enough of that, let's go right into reductions. As far as reducing agents go, we actually have it a lot easier than oxidation because we only really have 2 reagents. We have LiAlH4 and NaBH4. So when we split it up, NaBH4 is going to be weak, and LiAlH4 will be strong. And the reason that lithium aluminum hydride is strong versus sodium borohydride is weak, the way I like to think about it is that A comes before B in the alphabet. So A would be stronger than B. Might not make sense to you, but that's just what makes sense in my head. So hopefully that helps someone out. And what I want you to note is that lithium aluminum hydride reacts with both groups, whereas NaBH4 only reacts with group 1. And if you remember, group 1 is the more reactive group, and that makes sense because the weaker reagent has to react with the more reactive electrophile. But before we move on, we actually have one more surprise reagent, and we call him DIBA. And the reason I'm writing that in the middle is because DIBA over here is very interesting in that it is both strong and weak. And the way it works is it only reacts with group 2, but it stops at the aldehyde. And that will make sense in a moment once we do the reaction, but you have to know that reactants that react with DIBA will not go to completion, they will stop at the aldehyde. So if we actually try out these reactions, we can go ahead and start with group 1, which is aldehydes and ketones again. And starting with an aldehyde, we know that our reagent could be either NaBH4 or LiAlH4, just because we can. I'm going to say we're going to use NaBH4. So I want to point out a really important distinction. In this example, NABH4 is going to be our reducing agent. And our reducing species will actually be different. The reducing species is what's actually doing the reduction, aka your nucleophile, and that is your hydride ion. So make sure you know the distinction between the reducing agent and the reducing species, because Dr. West does tend to care about that distinction. And now we know that it will act like a nucleophile, so it's going to attack our electrophilic carbon. We're going to kick those electrons up to the oxygen. And now we have oxygen with an extra pair of electrons, therefore it has a negative charge. And we add our hydrogen here. Next up, we have H3O plus in solution. And so we're going to go ahead and protonate this oxygen. So it'll steal a hydrogen. And we are left with a handy dandy alcohol. More specifically, we have a primary alcohol, since this carbon is only attached to one other carbon. So we could say that when reacted with a reducing agent, aldehydes will always form primary alcohols. We see, though, that this is not the case with ketones, because if we have our hydride ion attack, kick those electrons up, we are now going to have our same intermediate where we get a negative charge. We add this hydrogen, and once more, we are going to protonate with H3O plus, and we end up with another alcohol, but now there are two carbons, and therefore it is secondary. And the reason for this is because we started out with a ketone. We have to keep those two carbons. You can't get rid of any carbons. So you end up with a secondary. And we can write this in again above here. And just to reiterate one more time, you cannot get rid of any carbons. So the aldehyde will keep its one carbon and become primary, versus the ketone will keep its two carbons and become secondary. And that is easy as pie. That is our group 1 reduction reactions. Before we dive into group 2 reactions, we actually have to cover one quick concept, which is hybridization. So just to review, the hybridization of this triple bonded carbon is sp. This double bond is sp2. And this single bond will be sp3. That's important to note because when we're doing a reduction or an oxidation, we're changing the hybridization. So if we go from an alcohol to a ketone, we go from sp3 to sp2. But if we go from a ketone to an alcohol, we are going to go from an sp2 to an sp3. This might not sound like a big deal, except you have to know that the more favorable change is towards sp2. So we're going to just ignore sp for now because that's not as important when it comes to these kind of reactions. But you do need to realize sp2 will be more stable than sp3. So if we ever have a chance to return to sp2 hybridization, we will. Now moving on to reductions, and why this is important is because, as I mentioned, we have a leaving group. But I'm getting ahead of myself. So let's start with our reducing species, our hydride. It will attack, kick up these electrons. And once again, we get an oxygen with a negative charge. And we've added this hydrogen, of course. And the concept I just talked about, sp2 versus sp3 comes into play because instead of protonating this right off the bat, we could actually instead reform the double bond to regain sp2 hybridization, and we kick off the leaving group. So instead of protonating, we have another step where we reformed the double bond and kicked off the leaving group. And now that we've done this, we actually have more H- in solution. So it will go in and attack once more and give us something we've seen before. And at this point, we have no choice but to protonate, since the oxygen does not have a leaving group to kick out. So once more, we have created a primary alcohol. So an ester that is reduced will create a primary alcohol. And just to note one more time, we have to use LiAlH4 for these reactions because the ester and carboxylic acid are less reactive. If we were to have used diba, this reaction would proceed only to this point and form the aldehyde and not go any further. Another reduction reaction that we're going to do is pretty much the same as what we did before, but now it's a cyclic ester. And this is a concept we will further cover later in the semester. But another word for a cyclic ester is a lactone. You might have heard that when talking about antibiotics and such. And this has the same exact concepts, except now the leaving group will not leave completely. It will just open the ring. So we are going to have the hydride attack again. But now I'm going to do this all in one step to kind of make it a little bit faster, but then I'll draw out the whole thing just to show you guys what all of that means. So we already know that we're going to kick those electrons up, but then we also know that eventually the electrons have to come back down to kick off this leaving group. So we could all in one step draw out the linear product, which has 1, 2, 3, 4, 5 carbons, and we had added a hydrogen, and we know that at the end of the chain we have an O- from the oxygen in the lactone that we broke open. And from this point we know that we have to protonate here, and also we have to reduce the aldehyde once more. So let's do those both at once. Bam. And also H3O plus is present, so we can go ahead and steal a hydrogen. And we then form our final product, which would be a primary alcohol from the carbonyl and an alcohol that was formed from the oxygen in the ring. Like I said, that's the fast way to do it, but now I am going to reset and do it the long way. If we want to do it the long way, we're still going to attack, but we're not going to open the ring yet. All that's going to happen is we have a negatively charged oxygen again, and we have a hydrogen present here. These electrons jump down and they will break this bond, opening up the ring. And always count your carbons. I'm going to start here, 1, 2, 3, 4, 5. So I know I have a 5-membered ring. Oopsie, I guess I can't count. So now on carbon 1, we have, on carbon 1, we have an O, rogue at the end, with a negative charge. And on carbon 5, we reform the double bond, and we have our hydrogen here. Now, we can go about this one of two ways. We can either protonate this hydrogen or this oxygen first and then move on to our second round of reduction, but I prefer to just do the reduction and then protonate both oxygens at once. Honestly, in nature, it happens a million different ways, so I'm just going to choose to do it the way that I find most easy, and that is to do this reduction, and we get an additional hydrogen added to this carbonyl carbon and a negatively charged, oxygen. And at this point, we know that we have H3O plus present, so we're going to protonate both of these oxygens, and we get our final answer. We have formed two alcohols, and in this case, they are both primary, but the one you want to focus on is this right here. And the reason for that is the alcohol that's formed from the carbonyl. The other alcohol is formed from the lactone ring, the inner ring's oxygen. And while they're both part of the product, so they're both important, usually we're talking about this one, since this can vary depending on what kind of substituents we have in the ring. It could be secondary or tertiary. But as far as this oxygen, it will essentially always turn into a primary alcohol. So now we are going to do the same kind of reaction, but with a carboxylic acid, and I'm gonna draw it out a little bit differently, just to make it kind of easier for you guys. So we know that H- is our nucleophile. We're gonna attack. Electrons go up, but we already know what's going to happen in the next step, right? The electrons are going to come back down to reform the double bond and kick off the leaving group. So we can actually draw that all in one step, so we don't have to draw a million steps in there. So we have our aldehyde, and then at this point, we know that another H- will come in, kick up these electrons, and now we will have two hydrogens attached to that carbon, and we have an O-, but that minus is going to get protonated by our H3O+, so I'm just going to go ahead and draw that final product for you. And that's pretty much it. It is essentially the same mechanism as our other reaction, so carboxylic acids will also make primary alcohols. Now, if we go on to these, all I want is to give a starting material and final product so that you guys can practice not drawing out the entire mechanism every time. So I'm going to change this one a little bit just so it's not the same example we just did. And now that we have this group, the first thing we want to do is number our carbons, as always. And so if we have an H- coming in to attack here, we know that the electrons go up, back down, and this will open. So I'm going to start out with a 5-carbon chain. And this is carbon 1, this is carbon 5. And so on carbon 1, I already drew the line for the OH. And we added 2 hydrogens since there was a leaving group. And off of carbon 5, we have a methyl, and we also have an O that'll turn into an OH. Now for the second one, our ring is going to stay the same in this example. It's not going to change. And the reason for that is we are not actually breaking anything open because we do not have a leaving group. So instead, all we're going to do is add a hydrogen to that carbon and turn the carbonyl into an alcohol. Moving on to this one right here, the H+, just like the last one we did, will attack, or excuse me, the H-, I don't know why I said H+. And the benzene ring will stay exactly the same. It's not going to change. The only thing that will change is we add a hydrogen to that carbon, and we turn the carbonyl into an OH. Last but certainly not least, the hydride ion will attack this carbon, kick up electrons, kick down the electrons, get rid of the leaving group. So we end up with a primary alcohol, And the product that we get on the side will actually be something we've talked about before. This is a phenol. Whenever he gives you something like this where you get a secondary product, you don't worry too much about the secondary product. It's just kind of like there, but it just doesn't disappear. That's why I wrote it out for you guys. The last thing we're going to do that has to do with reduction is an example like this. And I wanted to include this so you guys could practice with your condensed formulas, but I am going to draw this out for you now. So when we look at it, the first thing I want you guys to note is that this is a ketone and it's part of group 1. This is an ester and it's part of group 2. Excuse me, I wrote the wrong thing down. And if we remember from earlier, group 1 means it's more reactive and group 2 means it's less reactive. And if we very quickly talk about our reagents, we know that LiAlH4 is for both groups because it's very strong. NaBH4 is only for group 1 because it's weak, so it needs the electrophile to be very, very reactive. And diba is strange because it only works on group 2 and it stops at aldehyde. So with this information, all we have to really do is look at this molecule and see that the ketone was reduced, but the ester was not. Therefore, the only reagent that could make this reaction happen is NaBH4 because it only works for group 1, not group 2. And there it is. That's your answer. That's all I have for oxidation and reductions. Go back and practice these on your own, and that's it.